So let's work on it. Okay, yeah. Here, I use this diagram to show you how to merge two subarrays. Here, these two subarrays, each one has k elements. Yeah. A subarray and a B subarray. Yeah. We assume they are ordered. All right, so let's work on the comparison operations. Yeah. So how to work? Yeah. All right, yeah. The first time we compare A0 and B0, two smallest elements, A0 and B0. Okay, that's the first time. All right. And the smaller one, we use this notation, min 0. That is the minimum of A0 and B. So the minimum of the two elements, we know that should be the minimum of all the elements in these two subarrays, right? Yeah. That's the absolute minimum of all the elements we have here. So that element should be the first one in the final ordered array. Then the maximum, max 0, assume that is the max of the A0 and the B0, but that one, we do not know its position for the max 0. We know the min 0, we know the position of the min 0, that's the first one in the final ordered array, but we do not know the position of the max 0. Yeah. So we will find its position later. Okay, all right. So let us arrange sufficient empty locations for the final ordered array. So these empty boxes, so that's the locations for all the elements in our destination ordered array. Yeah. After the first comparison, the min 0, that one, we know it should be placed as the first element in our destination array. Min 0, yeah. The minimum of all the elements. By one comparison, we find the minimum of all the elements. So we put it in place. Yeah. The first position in our destination array, that's the right place for this element. Yeah. All right, so what is the next one? Next one, the survival, yeah, you know, whatever you like to call max 0. Yeah, the, you know, we do not know its position, so we need to do another comparison. Yeah, max 0. Yeah, here we consider that, let's say B0 is that max 0. Yeah, assume B0 is that max 0. Yeah. The next round comparison, next time comparison, we should compare A1 and a B0. A1 and a B0. Which one is smaller? The smaller one, and we use the min 1, the smaller one of A1 and a B0. Min 1 should be the second element in our destination subarray, right? Destination array. Yeah. So after our second comparison, min 1 is in place, and so on. Yeah, so you can see, yeah. Yeah. But it could be the min 1 could be B0, right? Whatever it is, if the min 1 is B0, then max 1 will be A1. So the next time we need to compare A1 and a B1 and so on. Yeah. So then we do this until we reach the end of the array. Yeah, because when we have last element left, we just put it in the last position. No comparison needed. No comparison needed. Yeah, because only one element left. We just put it in place immediately. Okay, yeah. After that, we get whole array sorted. Yeah. So let's look at how many comparisons do we need to merge these two ordered subarrays. Each comparison will place one element in place. But the last one, we do not need to do any comparison. Yeah. So you can see, yeah, for the worst case, 2k minus 1 comparison is needed. We need 2k minus 1 comparison. We have total 2k elements, but last one, we do not need any comparison. So the total number of comparison we need, 2k minus 1. Well, that's the worst case, not the best case. Okay, that's the worst case. The maximum number of comparisons we need to get two subarrays merged. Okay, yeah, all right. But here, let's consider worst case for the general merge step. Yeah, so what do you mean general merge step? The sizes of these two subarrays may not be equal. That's the general case. The size of the first subarray, n elements. The size of the second subarray, n elements. Yeah, they're not necessarily equal. Yeah, but we can still apply the same procedure as before, right? Yeah. So each time after one comparison, we just put one element in place. Except the last one. Last one, we do not need to do any comparison. Yeah. Now you can see for the worst case, how many comparisons we need for the worst case. You can see the answer is the total number of elements minus 1. N plus n minus 1. To merge any two ordered subarrays, it's worst case n plus n minus 1. Yeah, so that's the answer. Okay, yeah, all right. But how about the best case, right? Yeah. We just did the worst case, but how about the best case? Yeah, think about the best case. We do not need that many comparisons. Yeah. So think about what is the minimum number of comparisons we need for the best case. So that's also interesting. Yeah. Yeah. You need to imagine some scenario on the what special situation you can make the total number of comparisons to be the minimum you can have. Yeah, yeah. Think about some extremal case. Yeah. One extremal case you can imagine is, yeah, think about if B0 is greater than all the elements in A subarray. That's possible, right? B array is greater than any element in A subarray, or B0 is greater than the maximum, the last element in A subarray. If that happens, you only need to do comparison B0 with all the elements in A subarray. After you beat all of them, then the remaining elements B1 through Bn minus 1, you do not need to do any comparison, right? Yeah, because B0 already beats all elements in a subarray. After that, after you put all elements in a subarray in place, then you put a B0 in place. For the remaining B1 through Bn minus 1, you do not need to do any comparison. You just put them right in place in the destination array immediately. Okay, yeah. So here, the strategy, try to exhaust one of the two subarrays as early as possible. How to exhaust? Yeah, you just imagine the minimum of one subarray beats all the elements of the other subarray. When that happens, you exhaust all the elements in that subarray as early as possible. When that happens, you may get a minimum number of comparisons. Yeah. All right. So then the conclusion, yeah, exhaust, yeah, because you have two cases. You either exhaust the A subarray or exhaust the B subarray, right? Yeah, two possibilities. Yeah. So which one is better? Exhaust the shorter array is better. Yeah. Yeah. Because you can terminate earlier, right? Your algorithm can terminate earlier if you exhaust shorter subarray. Yeah. All right. So the conclusion for the best case efficiency, so that is the minimum of n and n. Minimum. This many comparisons for the best case, the general best case. Yeah. Okay. All right. Yeah. Because after this discussion, yeah, so we understand the merge step well. Yeah. So that's the standard merge step in this way. Yeah. All right. Yeah. 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 So now we complete the merge step. After we complete the merge step, we complete the merge sort. Yeah. So go back to our previous few slides, that divide and conquer diagram. Yeah. With that divide and conquer, even split with, this kind of merge step, we can get that merge sort. Yeah. All right. Yeah. But here I may like to make some comments. Yeah. But because some student ask me the question like, yeah, because based on the standard merge sort, we compare A0 and a B0 first. That's the standard merge sort. Yeah. But some students may ask me why we do not compare A0 and B0 and A minus 1 first. B0 and with the last element of A element. Yeah. Because if B0 can beat A and minus 1, then we only need one comparison. Yeah. So that's one student asked me this question last semester. Yeah. Yeah. Because for that special data, yeah, this way definitely you get the best solution. Yeah. But in the general case, you may get a worse. You may get a poor performance, right? Yeah. Think about it. So if A n minus 1 greater than B is yeah, you may go to backward, right? Yeah. A n minus 2 next, and so on. You may go backward like that, right? Yeah. So that means in the general case, you may not get better performance. Right? You only get better performance for a very, very special situation. Yeah, but not the general situation. Okay. Yeah. Yeah. So that may not be a good idea. Yeah. All right. Yeah.